we'll be able to talk about how a reaction can have different rates. So that's correct. I was like really confused by that. I thought I missed a typo. Now everyone's here experienced the situation where you want to get a chemical reaction to go faster. You just, it's a cold Saturday morning, you wake up tomorrow and it's going to be cold probably. And okay, first things, let's not lie to ourselves. Half of you aren't going to wake up in the morning. You're going to wake up probably 11 a.m. because you'll be staying up late tonight. But you wake up and you decide to make yourself a Milo, and you add the Milo and you pour in some milk, and you're like, why isn't this dissolving? You just get clumps of Milo at the top. Maybe you're not a Milo fan. Maybe you started to drink coffee already. And you're like, well, why is this not dissolving? And so you start to do things to make that Milo dissolve. Some people will go reach for the drawer and grab a spoon and stir it up and try and, get it to dissolve that way. Some people will reach for the microwave and put it in the microwave and heat it up, because if it's warmer, then it will dissolve a bit faster. All of these are ways that you guys naturally know to speed up a reaction. Some of you guys may instead be like, go to the tin and find that it's all in clumps. And so what you do is you break up the clumps before you add the milk. This is another way you can speed up a reaction. There are so many different ways that you can speed up a reaction. And you guys are all, you might not know it like instinct, you might not know the exact terminology for it, but you've all done things to try to make a reaction go faster. And so that's what the goal of this next part of it is to actually to sort of stop talking about different types of reactions, but to start talking about the speed of these reactions. And there are it's really annoying because of course there are some really good cracks that we would get you guys to do for this, but unfortunately, due to lockdown, we can't do those cracks. I'm just gonna have to sort of discuss the basics of it, at least now anyway. So let's go back. What did we do last time? Last time what we did was I went through solubility on Wednesday. We talked about all of the solubility laws. So we talked about what solubility means. Solubility means that it's something that is good at dissolving. It can dissolve in water. We talked about all alkalis, whether it's got an Na, a K, or an Li. If it's got one of these in front, it's going to dissolve, no matter what. If it's got something like NH4, or if it's got NO3 at the back, it's going to dissolve. By the way, see, I added this here, perfect for fertilizer, but also deadly explosive, so you got to be careful. So yeah, but then if we've got halogens, so ICl, these guys are almost always soluble, except when they're bonded to silver, lead, or mercury. Ag, Pb, Hg. So if you see something with a G in it or a B, you should be careful because they're probably insoluble. Sulfates, again, almost always soluble, but if you're bonded to a silver, a lead, and this time not mercury, but actually barium and calcium, so BaCa, it's not going to dissolve. And then the insoluble ones, carbonates, phosphates, sulfides, and hydroxides. None of these are soluble. But if you bond it to one of the ones that we've already talked about, then it will dissolve. So zinc phosphate doesn't dissolve. Titanium sulfide doesn't dissolve. Magnesium hydroxide doesn't dissolve. Thinking of another random metal, iron carbonate doesn't dissolve. Any of those, you cannot dissolve, they're insoluble. And then what we did was we said there are some that are on the borderline, but we sort of, we're not going to discuss it. I just thought I'd throw that up there for completeness. Here, we've got the rules written here. As long as you've got the rules written somehow in your book, then that's going to be useful. There are different ways to write down those rules. And then what we did was we got you guys to test yourselves and work on a precipitation reaction. So I said, swap these around, NaCl, that dissolves, CaCO3, ooh, that doesn't dissolve. So that's how you know the precipitate is going to be calcium carbonate. And then you could write down a full reaction for this if you wanted to. So now I gave you guys this to do as homework, and that's what we did period 1 today. So speed of a reaction, that's going to be our goal today, to talk about this. Already did that. So this is the first one. Reaction speeds. Okay, first things first. Chemical reactions can occur at different speeds or rates. Sometimes I will talk about the two of them differently, but we'll talk about different rates. So we talk about reaction rates a lot. But I thought I'd start off by talking about them as speed instead. Some reactions, like explosions, can happen in a matter of seconds, in even less than a second. Sometimes in milliseconds, like you can get a reaction of hydrogen and oxygen can happen in a millisecond or even shorter. That's how quickly they react. So you go from reactants to products in a matter of milliseconds. That's how explosions work. There are a lot of other reactions that work really, really quickly like that. But yeah, but some reactions, like the formation of rust, can take years, even decades. Another example of a reaction that takes a really long time is fermentation. So turning sugar into alcohol. And that's how we get like wine and beer and spirits and stuff. That takes a long time. It can take days. Sometimes it can take months. It can take, and you know, when food goes bad, when food rots, that can take a really long time. But if you're baking a cake, hey, that's going to take really quickly. That reaction happens very quickly. So some reactions go a long time, some reactions go really, really quickly. That's all I'm doing in this slide. I'm going to leave this slide up probably for another 30 seconds. If you guys need longer after that, let me know, but then I'm going to change the slide. And then we're going to talk a bit about some things that you should have learned from last year, but you may have forgotten. All right, I'm going to change the slide. We cool? Yay, nay?
Yeah.
Cool.
Yeah.
All right.
Yeah.
Yeah, cool. All right, let's go on. So, starting a reaction. So, reactions won't even start without two things. The first is reactions need enough energy to get them started. So, and that's sometimes referred to as an activation energy. Now, what activation energy means is the amount of energy needed to start a reaction happening. So that could be a spark, it could be the light from something, it could be it could be electricity that can also start a reaction, but you need to have some kind of energy at the start to get your reaction going. The other one would be you need to have enough reactants to keep the reaction going. So this is actually one of the other questions that a couple of people asked about, and I think David asked about this when we were working on the style, which was like, why does this reaction, you know, what's going on here? And the answer is this. For example, one of them was like, why does the hydrogen not burn? And the reason the hydrogen doesn't burn is because it didn't have access to oxygen. It needs to have access to that extra reactant, otherwise it won't burn. If you don't have enough of a reactant, or if you have no reactant, then the reaction's not going to go. Now, on the right here, we've got a fire, and this is a classic example of a fire is a combination of, is a combustion of carbon. Carbon plus oxygen goes to CO2. Hey, by the way, what type of reaction is this? Combination,
Composition?
composition, decomposition, single displacement, double displacement. So Alethea thinks.
Oh wait, no, wait. I think I got it wrong.
Combination.
Oh, it's combination.
It
Yeah,
is combination. Two small things are coming together to make a larger.
Wait, so is it combination or composition?
Are they the same thing?
I'm gonna say they're the same thing. Yeah, I think it's combination. I think it's composition. I actually don't remember. Doesn't matter. They mean the same thing. If you don't like it though, if you can't remember which one, then just say synthetic, because it's a synthesis reaction. So that's what it is. A synthesis reaction. That's another way you can talk about it.
Is it like a desynthesis?
No, there isn't a desynthesis. That's why
I like that dark theme though. Like, look at that. That's cool.
Yeah, that looks slick as a.
Yeah, look at the pen on fire.
Yeah, just keep it dark. I like it. It looks kind of cool, you know.
It's kind of like easier on the eyes, not gonna lie.
Oh, and that flame above it looks like, you know, it looks like a torch. Like, you know, if you think about it, it looks like a torch.
Yeah,
But the
Yeah,
So the attention to detail is
I
crazy.
do like it.
That's crazy.
Okay,
I
so
like it.
to start a fire, you need two things. You need a spark, that's going to be our activation energy. Our spark is going to be our activation energy, whereas the oxygen in wood and oxygen, that actually represents the reactants. So one way we use there are three ways to put out a fire, and two of them are these two here. One of them is to remove the oxygen by covering it up, so that gets rid of one reactant. The other one is to remove the fuel. So to move, if you've got a fire that's burning off gas, to turn the gas off. And that's one way you can put, if you've got a fire that's burning on paper, push the paper away. The other one would be, of course, to cool the fire down. But that's sort of not really here. But still, as if you can remove one of the reactants, then suddenly your reaction is going to stop. Anyway, so I've only got about 2 slides left. Can I change the slide, guys, or you guys need more time?
Yeah. I'm done.
If there's anyone that's ever, does anyone here that ever feels like a little bit of peer pressure, like, oh, I can't say that I haven't finished?
Oh my days, that's me every
No.
No, that's me in like other classes.
You can the advantage of this is you guys can privately message me in chat and just say, hey sir, I need a little bit more time. Don't tell anyone else. And then I can just be like, whoa, someone who shall remain nameless in chat needs a little bit of time. And that's really one of the advantages. You can't do that in real life class. You can do it here. But I'm going to change the slide now to the next slide. Unfortunately, yeah, I'm not going to have another black slide because I didn't have time to edit like too much stuff. But yeah, the next slide is just this here. But the pencil's still on fire. At a particle level, a reaction will occur if the particles collide with enough energy or activation energy, the particles are oriented in the correct way, and the particles are oriented in the correct way. I'm going to talk about what that means in a second. And then the bottom part is the extra little thing here. So I've only got 2 slides left, so I'm going to power through this one, and then I'm going to show you one thing on style that I want you guys to see, just because it's such a good animation. So firstly, the particles have to collide with enough energy. This is again linked to that activation energy. If those particles don't collide with enough energy, then they won't have enough energy to break the bonds and form new bonds. So you need to hit them with enough energy. So that's why you need that activation energy. You need that spark. You need that electricity to give your particles, or even just sometimes heat. Some reactions just go when you just heat them up enough. You need that energy to get those things to break their bonds and form new bonds. So that's what's happening here, is these two are bonding, and then they're breaking these old bonds and forming new bonds. So they're breaking the bond between blue and blue and between red and red, and they're forming new bonds. The other thing though is the particles need to be oriented the correct way. Now, we've never talked about, you guys have been doing little bits of chemistry here and there for about, for about 3 years now at school. And this is the first time I'm actually realizing this now, because this becomes such a big deal in a little bit of a big deal in year 12, but then when you get to university, it becomes so important. But even just the basics ideas, you actually learn all the way back in year 9. Orientation is important. If I was trying to react these, but I wasn't, if these are facing the wrong way, so if the blue one was left to right, it wouldn't work. If the blue one was if I was trying to react the blue one like this, it would not react. There wouldn't be a reaction. So part of the importance when you deal with chemical reactions is that they are lined up perfectly. Now, increasing the amount of collisions, or by ensuring, so because obviously if you want to make sure that, if you want to get these things to crash into each other, you could try and crash them into each other, and you want to make sure they crash into each other the right way. You could try and line them up perfectly. You could ensure their orientation is correct, or you could just slam 100 into them, slam 100 particles into them. Eventually, one of the particles will collide in the right way to get the reaction to work. And this, if you make sure that you've got enough energy and your orientation is correct, then you will speed up the reaction. It will actually make that reaction go faster. Now, are there any questions about these two ideas here? As I said, we're going to talk a little bit more about orientation in a second, but yeah, if the orientation doesn't work, it won't start. And if you're not enough energy, then it won't start. I'm going to give you guys a little bit of time to copy this down if you haven't copied it down already. I've only got
Wait, what? What happened?
okay, anyway, so the last slide is, let me just change slide, which is this one here. Now, this is a bit of a teaser for next lesson, okay? This is what we're going to spend the bulk of Wednesday's lesson talking about, but I thought I would start off by talking about it here. There are 4 ways to change the rate of a chemical reaction. And I love doing this with students because it makes it a lot easier just to go 1, 2, 3, 4. 4 ways, and you guys are just like, cool, that's all I have to memorize. The 4 ways of changing the rate or speed of reaction is, number 1, to change the concentration or the amount of reactant. Okay, if you want a reaction to go faster, if you're trying to get a room warm by burning by creating a fire, if you want to make the reaction go faster, just burn more wood, just add more reactant. If you want the second one, temperature. If you want a reaction to go faster, like for example, you could get bread to rise by just leaving it out on the table. But if you put it in a warm place, that bread will rise faster. If you put it in an oven, then you can bake it. That bread will rise even faster still. The third one is surface area. Now we're going to spend a lot more time talking about surface area, but surface area is how much space there is for it to react. You guys might know surface area from maths, like total surface area. In this case, surface area just means how much space is there to react. The example in the picture is actually an example of surface area. If you use powdered sugar, that can dissolve on your tongue like instantly. If you've ever had a sugar donut, it dissolves really, really quickly. But granulated sugar, like sugar grains, dissolve a lot slower. So how fine or how much surface area determines how quickly something dissolves in. The last one is a catalyst. Now, a catalyst is not something we've ever talked about before. So I don't expect you to know what a catalyst is, but in many ways, a catalyst is a magic ingredient that just sort of makes things go faster without changing the reaction. It doesn't get used up. You can just add a catalyst and it can make a reaction go really, 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 really fast. We're going to talk about what a catalyst does. And you guys have so many catalysts doing a good job in your human body right now. As I said,
Hey, what? What do we have?
You have catalysts inside of your body doing working right now to catalyze reactions.
What's that? What's catalyst?
Well, you'll learn about it. We'll talk about it next Wednesday. So you can look it up on your own if you want. But I'm just telling you guys, you got catalysts. There are some reactions that occur in our body that would take thousands of years to occur in nature. But because we've got catalysts, which are these special chemicals, they make the reactions go really, really fast. You guys have actually already studied the catalysts that we have in our body last year. They have a name. They're called enzymes. Enzymes are catalysts.
Oh my gosh, we learned this last year. Oh, sorry. Like, I
remember?
Yep.
You would have learned enzymes last year. You would have learned about, I think, renin is a catalyst. It is a special enzyme, but it also speeds up a reaction that would occur naturally, but it just, makes it go really, really fast. Okay. I'm going to now show you one last thing before we wrap up for today, which we've got about 2 minutes. I'm going to make this speedy. I'm going to get off this slide here. I'm going to jump over to here. I'm going to go back to style, but I'm going to go to, I'm going to go home. I'm going to go up to utensils. I'm going to open this for you guys to look at. Now, I don't want you to start it yet because obviously we're going to work on this on Wednesday, but I'm going to open this up in case you want to look at this yourself. But what I want to show you guys is this here is exactly what I was talking to you guys about. So here we've got two chemicals, right? We've got this molecule here and this molecule here. We're going to react the white one with the green one. Can you guys see this? Am I sharing the right screen here? Can you guys see the white?
Yeah.
Yeah, cool. So if I shoot the white one at the green one, and I shoot it like, let me see, if I just do this, right? Then nothing happens, right? The only way that I can get a reaction to work is if I give it enough energy. It needs enough energy. I wonder if this will work. No, not even that will work. It needs to have enough energy for it to break the bonds and form new molecules. So I need to break the bonds in both of them and form new molecules. But what if I hit it with that amount of energy, but I'm facing the wrong way? If I'm facing the wrong way, it doesn't matter how much energy I hit it with, it won't react. So therefore, you need to make sure not only do you have enough energy, but that you are facing the right way in order for the chemical reaction to work. And that's exactly what I went through in that other, that's exactly what I talked to you guys about in the other slide, where is it? Here. It's not just about having the activation energy, having the right amount of energy. It's also about being in the right orientation. Ladies and gents, that brings us to 3:05 or 3:04, but I'm done teaching
Right.
now.
Yeah.
So I'm pretty good.